There's sensitivity, there's specificity, there's true positive, there's false positive, there's true negative, there's false negative. It's very confusing. Well, that's what we have confusion matrix for. Ironic as it sounds, confusion matrix clears out the confusion regarding all these terms. Let's first take a sample data. Here we have data of rats eating cheese estimated based on their IQ levels. I love cheese. I don't know why some of these rats don't. Let's assume we use logistic regression as our model, which we will learn about in later videos. But for now, all we have to know is that logistic regression is a model to determine probability on an outcome, typically a binary outcome, which could be true, false, 0, 1, eats cheese or doesn't eat cheese in our case, based on an input variable, which in our case is IQ. First, based on some data, we got this curve, which we call logistic regression curve. Now let's assess the cheese eaters based on their IQs using this curve and compare that with the actual values. I'm going here with a threshold of 0.5, which means if a probability of a rat with certain IQ to eat cheese is greater than 0.5, then we consider that as a yes. And if it's lesser than 0.5, we consider that as a no. The rat with an IQ of 40 is estimated to be a non-cheese eater according to this curve. And the one with 80 is estimated to be a non-cheese eater as well. 110 lies somewhere here. And since that's less than 0.5, we consider that as a non-cheese eater too. And 120 is here, which is still less than 0.5. So that's a no too. Now the one with 125 lies here. So I would assume this rat eats cheese. And every other rat with the IQ above 125 is also estimated to be a cheese eater. Now let's compare our predictions with the actual values. We got most of these right. We'll assess our values and put it in this small little box called confusion matrix. If you see the graph about 0.5 threshold, I predicted 4 rats to be cheese eaters, out of which 3 are actually true cheese eaters, while 1 is a false positive. Similarly, I predicted 4 rats to be non-cheese eaters, out of which 3 actually don't eat cheese. But again, 1 is a false negative. Now these two cells, the top left and the bottom right, shows how good our predictions were. Well, this is for rats and their IQs, and it's all about cheese. But what if these predictions were done on patients with heart disease or even worse, cancer diagnosis? Some of these predictions can be dangerous. For instance, it would be insensitive to send back a cancer positive patient with a false negative report. And thus, sensitivity can be measured as true positives over all the positives, which is a sum of true positives and false negatives. Similarly, specificity is a measure of true negatives over all the negatives, which is a sum of true negatives and false positives.